So moving on from the idea that diffusion potentials create voltages, we'll take now a closer look at the resting potential and also think about electrochemical gradients. That is to say, how do we combine electrical and concentration gradients to figure out which direction an ion will move in. We have a cell here where we have an actual measured voltage of minus 74 millivolts inside negative in that cell. A cell sitting under conditions where the equilibrium potential for potassium based on the ion concentration gradients, let's say, is minus 90 millivolts. So how do we explain the fact that there's a difference between these voltages? In our compartment problem that was a perfect potassium electrode with just potassium moving, the voltage went to EK, and that isn't the case in this cell. The answer is that the measured membrane potential Vm will usually be a composite of several diffusion potentials, and the reason for that is because the membrane is usually permeable to more than one ion. The ion permeability is best expressed in terms of electrical conductance to reflect ion movement through ion channels. And when we do that, we can actually use a little expression here where the membrane potential is expressed as the weighted average of the ion equilibrium potentials for the permeable ions. And the weighting factors here is the fraction of the overall conductance G of the membrane that belongs to that particular ion. So if 80% of that conductance was due to potassium, that term there, GK over G total, would be 0.8. And any ion that has an open ion channel at that point in time would have an expression so that we could, in the end, have all of these fractional ion conductances adding up to 1.0. So if we take the example of the last cell there, and assume that 80% of the total membrane conductance was because there are potassium channels open at rest, but there were other channels open in that cell. There are a few, 5% of them are sodium channels, 15% of them are chloride channels. With those numbers, we could apply this little equation here, and the result would be minus 74 millivolts, the measured membrane potential in that cell. So the key concept in this equation is that there are only two kinds of variables that can change a membrane potential. Either we change an equilibrium potential, and that could only be achieved by changing the ion concentration gradients across a membrane, which are usually maintained very stable, or we can change the weighting factors. That is, we can open or close ion channels. And that's physiologically how membrane potentials are regulated. Just some terminology there around changing membrane potentials. We use the word depolarization to mean a change to a less negative membrane potential difference. We would use the word hyperpolarization when the membrane potential difference becomes more negative. And we would use the word repolarization for events that return the membrane potential towards the resting potential value. Turning to the electrochemical gradient for an ion, this is the net driving force for ion flux, and it's a combination of the voltage across the membrane and the ion concentration gradient. The problem here is how do you combine units of millimolar concentration and units of millivolt electricity? And the answer is the Nernst equation. Because what we've seen is that we can take a concentration gradient across a membrane and we can express the strength of that concentration gradient in voltage units by applying the Nernst equation. It's really what I call a currency converter, converting a concentration gradient into a voltage. And now we can combine these two together. If you were ever asked to figure out which direction an ion is moving in, whether it's moving into or out of a cell, one way to do this is to use the mathematical convention. The gradient is the membrane potential minus the equilibrium potential. By convention for cations, a positive value of this equation here is an outward flux or an outward current, and a negative value will give you an inward flux or an inward current. And then for an anions, the reverse would be true, that a positive value implies an inward flux and a negative value is an outward flux. Should you ever be required to think about which direction an ion is moving in, though, I would suggest instead of doing mathematics, you take a look and compare the voltage to the equilibrium potential, and then ask yourself, which way would my ion have to move to move from the voltage towards its equilibrium potential. Let me give you an example. If you had a membrane potential, like in our example, of minus 74 millivolts, and you had a potassium equilibrium potential of minus 90 millivolts, which is more negative, imagine you opened lots more potassium channels. How is the cell going to move a potassium ion to get from minus 74 towards minus 90? The cell has to get more negative, and so in order to do that, potassium ions would have to leave. So that would be an outward flux of potassium ions. If we did another example, let's say we have a cell with a membrane potential again of minus 74 millivolts. But let's say now this cell opens a bunch of sodium channels, and we saw that equilibrium potential for sodium is way up at plus 67. What would happen in this case is the cell will try to move its membrane voltage from minus 74 towards plus 67. How do I get much more positive by moving sodium ions? I move the sodium, the positive ion, inside to make the cell more positive. In this situation, sodium flows into the cell. So looking at this qualitatively, I think gives you a clearer understanding of how fluxes would work. The difficult one is always anions. So imagine we had a cell where, again, the membrane potential, let's let it be minus 74 millivolts, and let's take an E chloride value for a non-excitable cell. We saw in a table in the last presentation of around about minus 50 millivolts. If I open lots of chloride channels in this cell, it will try to move from minus 74 towards minus 50. The cell has to become less negative. How can I move a chloride ion to become less negative? I have to move a chloride ion out of the cell to make the cell less negative. In the next session, we'll talk about action potentials.